Your phone says you're on the highway, then the blue dot jumps into a field and refuses to come back. The map is suddenly confidently wrong. At the same time, a jet on a polar route tries to raise voice radio and hears nothing but crackle. In a power grid control room, operators notice alarms tied to strange currents flowing where they shouldn't. No one is hacking you. Nothing exploded in space. One short alert explains it. Space weather is active. Here's the unsettling part. These failures can share one source. The sun can send energy and charged particles toward Earth, and Earth's magnetic shield can turn that hit into problems in our atmosphere and infrastructure. The same solar outburst can confuse navigation, strain communications, and stress the grid, all without a single storm cloud. Space weather is the changing conditions in space driven by solar activity that disturb Earth's magnetic field and upper atmosphere. When that happens, radio signals, satellite navigation, and power systems can struggle. Forecasters treat it like a forecast problem, issuing alerts and warnings to describe what's happening and what impacts are possible. They group impacts into three big buckets. First, radio blackouts, when the ionosphere changes so quickly that certain radio signals fade or vanish. Second, radiation storms, when energetic particles raise radiation levels in space and at high altitude. Third, geomagnetic storms, when solar wind and magnetic structures from the sun disturb Earth's magnetic field and drive electrical effects on the ground. Think of it like this. Earth lives inside a magnetic bubble. Most days, that bubble is calm enough that we never notice it. On storm days, the bubble shakes, and our tech shakes with it. Solar flares are sudden blasts of energy. Their light and X-rays arrive fast, so effects can begin on Earth's sunlit side within minutes. That energy can change the ionosphere and trigger radio blackouts for some frequencies. Coronal mass ejections are huge clouds of magnetized plasma thrown from the sun's outer atmosphere. They travel far slower than light, often taking about 1 to 3 days to reach Earth. When they hit, they can drive geomagnetic storms that change Earth's magnetic field rapidly. That rapid change is what can push unwanted currents through long conductors on the ground. Solar energetic particles are high-energy particles accelerated during solar eruptions. They can raise radiation levels in space and at flight altitudes, especially near the poles. That is why aviation and satellite operators watch radiation storms closely during major activity. Now we follow the damage like a detective. One chain for GPS, one for flights, one for the grid. GPS and other global navigation satellite systems work by timing radio signals from satellites. Your receiver listens to signals from several satellites and uses tiny differences in arrival time to estimate distance. Combine several distances and you get a position. But those signals must pass through the ionosphere, a charged layer of the upper atmosphere that can slow and distort radio waves. GPS uses models and corrections to reduce that error. On quiet days, those corrections usually work well enough that you never think about the sky above you. During strong space weather, the ionosphere can become uneven and turbulent. Charge density can change in patches, and the signal can flicker as it passes through. This is called ionospheric scintillation. When it is severe, a receiver may struggle to keep a stable lock on satellites. Accuracy can drop, positions can jump, and in the worst moments, the receiver may fail to produce a reliable fix. Here's the simple mental image. GPS needs a clean time ruler. Space weather can warp the ruler, and sometimes it can shake the ruler so hard the receiver stops trusting it. And GPS is not only where am I, it is also what time is it. Precise timing from satellite navigation is used as a reference in many timing-sensitive systems, so ionospheric chaos can matter beyond directions on a screen. Long-range aviation relies on communication and navigation that must work over oceans and remote regions. One weak link is high-frequency radio, which can travel far by reflecting off the ionosphere. That reflection depends on the ionosphere being in the right state. When a solar flare hits the sunlit side of Earth, it can rapidly change the upper atmosphere in a way that absorbs high-frequency radio. The sky becomes a sponge for those signals. The result can be a radio blackout for high-frequency communication. Polar flights are especially sensitive. During severe space weather, high-frequency communications can become unusable during polar operations. When that happens, airlines may reroute flights to lower latitudes, adjust altitudes, or use different communication procedures. Those changes can cost time and fuel, but they help maintain safety and coordination. It is not only communication. Navigation performance can also degrade when the ionosphere is disturbed, and some satellite-based services can become less reliable. That is why aviation treats space weather as a whole environmental hazard, not a single equipment issue. The power grid is a massive conductor spread across continents. During geomagnetic storms, Earth's magnetic field can change quickly, creating electric fields. These fields can drive geomagnetically induced currents through long transmission lines and other infrastructure. This sounds unreal until you remember a basic rule of physics. Changing magnetic fields can create electric fields. When Earth's magnetic field shifts during a storm, it can create voltage differences across huge distances. Long transmission lines become pathways where those voltages can push current. These currents are dangerous because they act like slow, almost direct currents entering equipment designed for alternating current. In large transformers, that can cause extra heating, strange harmonics, reactive power problems, and protection system complications. Even when nothing breaks permanently, the grid can be pushed into unstable operating conditions. The grid doesn't have to burn to fail. If space weather pushes it into an unstable corner, a chain of smaller problems can cascade into a blackout fast. To the public, it can look like the power simply died. The real story can start far above the atmosphere. When Earth's magnetic field is disturbed, energy pours into the upper atmosphere near the poles. That is why major storms can produce intense auroras. But that same energy can heat the upper atmosphere and change conditions that satellites fly through. The atmosphere can expand upward when heated, increasing drag on satellites in low Earth orbit. More drag means more resistance, which can change orbits and increase tracking and operational workload. So auroras are not the event, they're the scoreboard telling you Earth's space environment is under stress. Beautiful doesn't always mean harmless. This is not hypothetical. On March 13, 1989, a major geomagnetic storm caused widespread effects on power systems, including the Hydro-Quebec blackout. It is still studied as a modern warning sign that geomagnetic storms can affect large-scale infrastructure. The Carrington event of 1859 is the classic extreme storm. In the telegraph era, electrical systems behaved strangely and operators reported shocks and fires. A storm on that scale today could severely disrupt satellites and communications and could cause large-scale blackouts. It is often used as a benchmark for extreme planning, even though scientists debate exact details and how often an event that intense may occur. And on May 10 to 11, 2024, forecasters described an extreme geomagnetic storm, the strongest in over 20 years. That real event raised concerns about communications and navigation. Solar activity rises and falls in an approximately 11-year cycle. Around solar maximum, sunspots, flares, and coronal mass ejections become more common. The sun's surface becomes more active and complex, and the odds of Earth facing a major outburst increase. That does not mean constant danger. It means higher odds that a strong event lines up with Earth, and the quiet background we take for granted becomes noisy. Space weather forecasting has a hard problem. We can often observe eruptions on the sun and estimate arrival time, but the most important factor for geomagnetic storm strength is how the incoming magnetic field connects with Earth's field. If the incoming field couples strongly, impacts can be much worse. If it couples weakly, the storm can be milder, even if the cloud is large. That detail becomes clearer closer to arrival when spacecraft sample the solar wind directly. That is why upstream monitors matter. They can detect changes before they hit Earth, sometimes giving operators a short but valuable reaction window. When forecasters warn of space weather, different industries have playbooks. Power operators can increase monitoring, adjust loading, and follow reliability procedures built around geomagnetic disturbance risk. The goal is to keep the system away from fragile operating states and spot abnormal currents early. Aviation can use official advisories, plan around polar communication constraints, and adjust routes or altitudes when conditions warrant. For GPS-dependent work, mitigation is often built into professional systems through monitoring, correction services, and receiver designs that help manage ionospheric errors. For everyday life, the takeaway is simple. During major events, navigation and radio behavior can degrade for real physical reasons. Checking official alerts can explain why your device suddenly seems unreliable, and it can remind you to cross-check with other information when precision matters. Space weather is the sun's way of reminding us that modern life is built on invisible links, radio waves, satellites, and long wires. Most days, the space around Earth is calm. On storm days, it can reach into your pocket, your flight path, and your light switch all at once.